Okay, so part 2 in our programmable systems about microcontrollers is going to be using Yenka to simulate microcontroller systems so that we can actually see them working. So using Yenka, we'll always start with the same thing, remember, we always start with the component tree. So you would browse and you would go to pupil share, technical, engineering science, and there's a component tree. And this is where we've given you a Yenka document that has all of the components that we use in the course. So it misses out, there's loads and loads of components in Yenka, so we miss all of those excess ones out, and we've only got the components that you'll use in National 5 and the component tree. You should already have used this by the time you get to programmable systems, so this should be familiar to you. The idea is that we've got individual use things here, so there's a thermistor. If you need more than one thermistor, you would copy and paste it. Avoid deleting your last one. If you don't need that, just put it back in the tray. So when you open up component tree, you'll need to save as and save a copy of this in your own directory. So you should have a folder on your desktop or in your documents that's got something to do with engineering. I've got a wee engineering work in progress there. So you'd always save it in there and call it whatever it is, and we're going to call this one microcontrollers. This is going to be our first microcontroller file, and then we can edit it. You can see the name changes to microcontrollers now rather than component tree. What we've got is our 18M2 down here, so we can pull that out. We always need to use an 18M2, remember. And then, as we've seen in the previous video, we're going to create flowcharts to get this microcontroller to do what we need to do. So what I want you to do is, I want you to copy along with me here. So this is a video that's really for use in school, on the school premises, although if you're working at home, you can download Yenka for free. So I want you to copy along here. So I've pulled an 18M2 out. If you're working from home, where would you find the components? You'd find them in this objects folder here. Make sure you're on picks. If you're not on picks, you can change it. Alright, so make sure you're on picks. And then you've got pickaxe. There's the 18M2. You would drag that guy out. And there's all your flowchart elements here. So every flowchart element I find out over here, you'll be able to find in these folders here. Okay. We've always got to have a start bubble. We pull a microcontroller out and then we pull a start bubble out. If I hover over that start bubble, you can see that it draws a line to the microcontroller. What this is letting us know is that Yenka knows that that microcontroller is going to run whatever commands we put here. I'm going to keep it super simple. I'm going to change the state of the output pins. So I've joined that on there. Now when I move that about, it's got a wee line. With these flowchart symbols, they're connected logically. Most flowcharts have one input and one output. You can send an output to one location, but you can receive an input location from a bunch of different places. There's more than one way in, but there's only ever one way out, you know. So set outputs, how do I set the outputs? I just click on that and it lets me change any of those output pins. We can either turn it off, on, toggle, which means just change it from whatever it was. If it was on, make it off. If it was off, make it on. Or we can make no change to it at all. So I'm going to go, let's turn pin 7 on. And then I'm going to put a delay in. We will use delays quite often with microcontrollers because it's one of the principal ways that we can problem solve, where we can identify if the microcontroller is doing what we need it to do. As I've mentioned before, microcontrollers are super fast. They'll carry out controls once every 4 microseconds in this case, in the real world. If it's doing something wrong, chances are we wouldn't see it doing something wrong. So in order to slow it down, sometimes we put delays in. Remember, this is hardware programming we're doing, so in a lot of cases, like if we want to turn a motor that's attached to a paddle in a vat, and it's controlled by a microcontroller, we might use a timed delay to keep that motor running for however long it needs to run to do its job. In this case, I'm just using it to slow it down so that we can see the microcontroller doing its job. So I'm going to turn pin 7 on, I'm going to wait 5 seconds, I'm going to turn pin 7 off. I need another one of these, so I'm just going to Control C, Control V. I'm going to change it so it's turning it off now. and then I'm going to stop my set of instructions. It's a wee bit kind of, it's not very neat. Could look a wee bit nicer. So there's my instructions. I've got a wee play button up here. So if I press play, that microcontroller will play out that sequence of events. And what we should see is something changing on pin 7. Oh, it goes on. It stays on for 5 seconds. See that wee red dot indicates that there's a voltage there. And then after 5 seconds it goes off. The microcontroller reads the stop command and finishes. Now the truth is, having a stop command in a microcontroller is a bit pointless, because that's all that microcontroller would ever do. The minute you provide it power, it would turn pin 7 off, wait 5 seconds, turn it off, never do anything ever again until you remove the power supply and then turn the power supply back on. So the stop command's quite uncommon to be used. So you go ahead and build that in Yenka for me, please. Now, that's an example of, you should have paused the video to build it. That's an example of, so if you haven't built it, pause it now and build it. That's an example of a sequential circuit, a sequential set of instructions that are carried out one after the other, and it comes to an end. As I said, pretty uncommon to see that. All we're doing is turning on pin 7 and turning off pin 7. We could have any device connected to pin 7. I'm just going to connect a wee, it's a diode, don't want a diode, I want a light emitting diode. Let's connect a wee light emitting diode there. And a wee 5 volt supply. Whenever you're using microcontrollers, any supply voltages that you use should be 5 volts. So the LED comes on for 5 seconds and then it goes off. Got a transducer driver in there. The transducer driver is receiving from the microcontroller. That's what allows that LED to come on. We could have in that LED and resistor. We could have a motor, a solenoid, a bulb, whatever. All sorts of stuff. When you are responding to problems, the problems will have context. Right now I'm just messing about with simple circuits. So that's our first introductory flowchart and code. It's pretty self-explanatory how to turn pins on and off and things like that. As I'd said, the stop is super uncommon. It's far more common to have what we call an infinite loop, where the code is carried out over and over and over and over again forever as soon as you turn the power on. In that case, we wouldn't have a stop bubble. In this case, we would have a line just drawn back to the start again. So after that output 7 off command, we come around here. Now here's a wee thought experiment for you. What's going to happen when I press this play button? What's going to happen? What you'll think is that output 7 will come on, it will be on for 5 seconds, it will go off, and then it will go back on again for 5 seconds, and then it will go off. But what you're not seeing, the issue that you're not seeing is, how long is it going to be off for? Because we turn it off, and then the next thing that happens is we turn it back on again, with nothing in between them. This microcontroller acts super fast, every 4 microseconds. 4 microseconds is absolutely crazy. Let's put that in context. So what I've got here is a reactions tester. Find out how fast your reactions are, or how old are your reactions. In a moment you'll start driving. When you see the stop sign, click or press any key to stop and you'll guess your age. Let's see how old my reactions are. .571 milliseconds, right? So my reaction was half a second. I mean, that's crazy slow. 49 years old, I'm younger than that. I'm a bit tired today. 571 milliseconds. Let's see if I can get that down to 400 milliseconds, because that'll make my maths a bit better. Right, come on. Faster, faster. 574, wow. The microcontroller could react in 4 microseconds. That's, if we convert that milliseconds to microseconds, that's 574,000 microseconds I'm reacting in, and it could do it in 4 microseconds. So, you know, what's 574 divided by 4? Let's not embarrass myself by doing mental maths for that. 143,000 times faster than me. as a microcontroller. I'd expect your reactions to be a bit faster than that. I think you could be down at about 200 milliseconds. Still going to be, a microcontroller still going to outstrip you in terms of its reactions. So when we look at that Yenka file, it's going to go off and then come back on again 4 microseconds later. So to you, that's an unfathomably short period of time. You ain't going to see that on and then off and back on. Now on Yenka we do see it, because Yenka does us a favour. Yenka slows the microcontrollers down for us because it knows that we would have difficulty seeing it. Plus, it would have difficulty simulating it that fast. If you go into the space properties, you can go into Flowcharts, and it's set to auto step every 200 milliseconds rather than 4 microseconds. And we can't even get as fast as 4 microseconds. The quickest we can get Yenka to simulate these microcontrollers is 0.5 milliseconds. That's 500 micro. That's still over 100 times slower than a real microcontroller. But you can see there, every 5 seconds, output 7 just seems to flicker a little bit. Yeah. In a real life microcontroller, you wouldn't see that light go off and back on again. So you need to watch out for that in microcontroller circuits, particularly in circuits where the SQA perhaps asks you to turn a pin on and off with an equal frequency. You would have to have another wait after it. I'm going to slow these. I'm going to ditch these 5 seconds because that's taking too long. I'm going to go 1 and 1. So we'll now be able to see that light remain off for a wee bit before it cycles back to being on again. On, off, on, off. And the difference is we are now controlling that frequency, and we're using an infinite loop to do it. So go ahead and build that circuit now for me, please. Okay, so here's a simple problem. There's an 18M2 with 2 output devices. It's got a bulb and a motor, and there's a little specification. The motor is to come on first, and then 3 seconds later the light is to come on. It stays on for 1 second, and then 4 seconds later the motor goes off, and it's all spelled horribly wrong. Let's fix that way over here. The motor goes off. So notice that this doesn't mention anything about looping. It doesn't say anything like, and the whole thing keeps happening again and again and again. It doesn't say that. This is an example of a code or a flowchart that's required that ends with a stop. These things have to happen, and then that's it, over. So I would like you to try to create that flowchart. Notice what pins they're connected to. So that transistor for the light bulb is connected to pin 5. So if you want to pin the light bulb on, you'll need to turn on pin 5. If you want to turn the motor on, you'll have to turn on pin 2. And you'll have to use delays. So you'll have to use a start, you'll have to use a set outputs bubble, you'll have to use a delay bubble, and you'll have to use a stop bubble in order to create that. So what I'll do is I'll save this file in the pupil share. Okay, so I've saved it as microcontroller simple problems, and it's in the pupil share. Does this tell me where it is? That's a bit rubbish. It's in pupil share technical engineering science people, electronics and control, programming files, and it's called microcontrollers simple problems. So you can open that file and complete this problem. Make sure you show your teacher the answer so that they can check and make sure you're correct. What I'll do is I'll add another few on here, and you can complete them as well. So we'll maybe have 4 different ones, but they'll all be roughly the same. They might require a stop bubble, or some of them might require a loop to continue over and over again, but you can just rewind the video to see them. Okay, so I've saved this with 4 questions in it. What I want you to do is just create the flowchart for each one next to it. When you create the flowchart, make sure that you point the start bubble at the correct microcontroller. So like you put a start bubble out there, click and hold on the wee microcontroller and point it at the microcontroller that you want to run that flowchart. So this microcontroller is going to run that flowchart. Every time I pull a new start bubble out, when you point that microcontroller, just click and hold and drag it onto the microcontroller that I want. So when I put a new flowchart down here, drag it and point at that one. Also, for the sake of memory and things running well, only have one flowchart running at a time. You know, don't have all 4 play buttons pressed, or Yenka will slow it down. And make sure that you've double clicked in Eureka and set it to quick step, otherwise some of these will be really, really slow. So the first one is this one here, the motor's to come on first. Then 3 seconds later the light is to come on, and then 1 second later it's to go off, and then 4 seconds after that the motor goes off. So just sequential, with no loop required. The second one is this one, when I've added in a solenoid. There's now 3 devices. Just essentially the same style of question, just more things to take account of. So both the motor and solenoid come on first. Remember, when you pull out one of these set outputs boxes, you can change multiple pins at the same time. You don't have to use it just for one. Every time you add a change on it, just adds it into the box. So you can do loads of changes in the one box if you want. Alright? So if you've got multiple outputs changing at the same time, you can change them at the same time in that flowchart symbol. So both the solenoid and the motor come on first. 1.5 seconds later, so you just put 1.5. You can put decimals into that delay flowchart symbol. 1.5 seconds later the bulb comes on and the motor goes off, so 2 things happen in that one. 3 seconds later the solenoid goes off, 2 seconds later the bulb goes off. So again, just a sequential set, no need for a loop, should have a stop bubble in at the end. The third one is down here. Here's the third question, so you have the flowchart sitting here. Make sure you point that start bubble at that microcontroller. The bulb is to come on for 0.7 seconds and then go off. The solenoid is to come on, so that would happen immediately. There's no time delay in between them, so the same time that the bulb goes off, the solenoid comes on for 0.7 seconds and then it goes off. The system is to repeat forever. So basically it's bulb on for 0.7, solenoid on for 0.7, and just keep going. No stop bubble in this one. Okay. The last one, bit weird. Last one's a wee bit weird. So the bulb is to come on and then go out, and then nothing should happen for a second, everything off for a second. And then the motor comes on for a second and goes off, and then the solenoid comes on for a second, goes on. So it's motor for a second, solenoid for a second, over and over again. So notice there's a bit about the bulb in at the start. You can't put a loop right back to the start, because if you put a loop right back to the start, that will include the bulb coming on for 1.2 seconds and then going off for a second, and that bit's not to be in the loop, so you need to make sure you bring your loop back to an appropriate place. I've actually built it here and I've hidden it so that you can't see the flowchart, but I can run it so that you can see what's to happen, so that you really understand the question. Bulb comes on, goes off, nothing happens for a second, then the motor, and then the solenoid, and you can see they're just alternating between each other. The motor's always got that symbol that it's running, but you can see that it's either speeding up or slowing down. When it's switched off, the motor slows down. The motor doesn't stop straight away, it takes a while to go all the way off. So the exercise looks like a flowchart next to each microcontroller circuit, with the flowchart pointing at the correct microcontroller and the output devices doing whatever they should be doing based on what's in the text box whenever anyone presses the start button. Okay, this is saved in the pupil share microcontroller simple problems. Go ahead and do that now, let your teacher see it.